All right, May the 3rd through the 7th, we are on lesson 35, so make sure you have that one out in front of you. You do have a piece of graph paper that is in your pocket. Make sure you have that with you because you're going to need it here in just a moment. So the first question states that write the equation of two parabolas that are congruent to y is equal to x squared and explain how you determine the equation. If you remember, all parabolas are congruent to the graph of the equation y is equal to 1 over 2p x squared. We figured this out the last week. So if the distance is 1, I would substitute that in for p. And so therefore, I could write an equation y is equal to 1/2 x squared plus 1. Or y is equal to 1/2 x squared plus 2. Alright? Number 2, sketch a graph of y is equal to x squared and the two parabolas you created on the same coordinate axes. Go ahead and do that. I'm not going to spend time graphing it. I want you to go ahead and graph it and look and see what you get. Alright, number 3, write the equation of two parabolas that are not congruent to y is equal to x squared. Y is equal to 2x squared. Y is equal to 4x squared. Our distance is not the same. Alright? Sketch the graph of y is equal to x squared and then the two parabolas that you created. So go ahead and do that on your graph paper. And then use your work in exercise 1 through 4 to answer the question posed in the lesson title. Are all parabolas similar? Explain your reasoning. Alright, so what you're going to see is after you have looked at the fact that when we change the a value in our parabola equation, the graph is basically the same shape. Alright? You do have to make sure that you have your graphs when you turn your work in. So make sure you have that. However, when we change things, we dilate them. You will see that some of those are a dilation of the original graph. They may be narrow, they may be wider, something like that. Alright, so do you think they're all similar? So answer that question, and then that's what we're going to be working through today. We are going to be working through, do we think that all parabolas are similar? Alright? Move the camera just a little bit here. Alright. So a lot of this you are on your own doing. Now let's look at number 6. Alright. So the parabola at the right is the graph of what equation? A, label a point xy on the graph of P. Alright, so our parabola is P. We are going to find a point of xy on that parabola. Alright, so it doesn't matter what point we choose, but we'll choose this point right here. Alright, and this is xy. What does the definition of a parabola tell us about the distance between the point xy and the directrix L, and the distance between the point xy and the focus? Alright, now, I don't know if you can see your directrix, but here is the directrix. Alright? So, the definition of a parabola tells us that the distance from my point xy to the directrix is equal to the distance from the point to the focal point. Alright? So the distance from the point xy to the directrix, excuse me, is equal to the distance from the point xy to the focus. Alright, that's what we've been doing for the last 2 lessons. Create an equation that relates these 2 distances. Alright, well let's look. My focus point is at 2, 0. Alright. So my distance from xy, so the distance from xy to the focus would be the square root of x minus 2 squared plus y minus 0 squared. Alright? The distance from xy to my directrix, or L. Alright? Well, let's look at our directrix. Our directrix is at x is equal to -2. In this case, the point here of our focus, of our directrix, has the same y coordinate. Alright? So I know that the x is -2, and it has the same y coordinate. So I would subtract my x's, so therefore x minus a -2 would be x plus 2. Alright, so therefore, here's what I can do. I can set x plus 2 equal to the square root of x minus 2 squared plus y minus 0 squared. Alright? Now it says solve this equation for x. Alright, so let's go ahead and solve that. So I have x plus 2, and I have to square that to get rid of the square root. So I have x minus 2 squared plus y minus 0 squared. Alright, so let's go ahead and square x plus 2. So x times x is x squared. X times 2 is 2x. 2 times x is 2x. 2 times 2 is 4. X times x is x squared. X times -2 is -2x. -2 times x is -2x. And -2 times -2 is +4. And then I have y minus 0. That 0 doesn't exist really, so I'd have y squared here. Alright? Alright, so then let's go ahead. X squared plus 4x plus 4 is equal to x squared minus 4x plus 4 is equal to y squared. When I take the x squared over, they zero out. Alright? When I add the 4x they zero out. So I have 8x is equal to y squared. Now if you remember, it says to solve for x. So I need to divide by 8. So I get x is equal to 1/8 y squared. Alright, so I know that P in terms of, and we would write it like this, P in terms of xy would look like this. X is equal to 1/8 y squared. Alright. Find 2 points on the parabola P and show that they satisfy the equation on part D. Alright, so if I look at this, I could do 2, 4, and 2, -4. 2, 4, and 2, -4. Because I can see that those points are actually points on my parabola. So let's go ahead and plug it in. So 2 is equal to 1/8 times 4 squared. So that would be 2 is equal to 1/8 times 16. So I would get 2 is equal to 16/8. 2 is equal to 2. That works. Alright, let's plug in the second one. So I get 2 is equal to 1/8 times -4 squared. 2 is equal to 1/8 times 16. 2 is equal to 16/8. So 2 is equal to 2, and that satisfies the point. Okay? Alright. In the previous exercise, is P a function of x? No, because the x value 2 corresponds to 2 y values. If you remember, in order to do functions, it would have to pass the vertical test. So the vertical line test. So if I took a vertical line and passed through, I would see that my x point crosses or has 2 y values. So therefore, it is not a function of x. Is P a function of y? Well, so then let's look at that. If we rotate the plane by 90 degrees, we would see that we have a function. Alright? So in other words, if I turn my plane 90 degrees, then yes, I would have a function. Alright? What have we learned about the definition of a parabola? The points on a parabola are equidistant from the directrix to the focus. That is the one thing that we have learned about a parabola. What transformations can be applied to a parabola to create a parabola congruent to the original one? Well, if the directrix and the focus are transformed by a rigid motion, in other words, a translation, a rotation, or a reflection, then the new parabola defined by the transformed directrix and focus will be congruent to the original. Alright, so essentially every parabola that has a distance of p units between its focus and directrix is congruent to a parabola with a focus of 0 and 1/2 p. Alright. So, all parabolas have the same distance between the focus and the directrix are congruent. Alright, so how many of you think that all parabolas are similar? And tell me why. Well, let's talk about what we know about the word similar. In geometry, when we talked about similar, then we knew that if I could do some sort of transformation that would take one figure onto the other, then it could be similar. Alright? What could we do to show that two parabolas are similar? Since every parabola can be transformed into congruent parabolas by applying one or more rigid motions, then perhaps similar parabolas can be created by applying a dilation, which is a non-rigid transformation. Alright, so let's answer these two questions. So, similar in geometry, two figures were similar when we could transform or do a transformation to take one figure to the other. Okay? So what could we do to show that two parabolas are similar? Well, maybe we could do a non-rigid motion, a non-rigid transformation, or one or more rigid transformations. Or a non-rigid transformation. Like a dilation. And I misspelled that. I can look at that and see that. Dilation. Alright? So to check to see if all parabolas are similar, we only need to show that any parabola that is the graph of y is equal to 1 over 2px squared, for p being greater than 0, is similar to the graph of y is equal to x squared. Alright, so let's talk about how to do that. Alright, so we have what we call a vertical scaling. Alright, a vertical scaling. A vertical scaling of a graph by a scale of the factor k is greater than 0 takes every y value of the points x, y on the graph of y is equal to f of x to ky. The result of the transformation is given by the graph y is equal to k f of x. Okay? So, we're going to take k is greater than 0, alright, and it's going to take every x, y point on the graph, or every y value of the x, y point on the graph to ky. So then we end up with y is equal to k f of x. So I'm going to multiply my function by k being greater than 0. Alright, we have what we call a horizontal scaling. Alright, this deals with our y coordinate. Alright, the horizontal scaling of a graph, k is greater than 0. Alright, and it takes every x value of the point x, y, and the result looks like this. Y is equal to f times 1 over kx. All right? Now, what does that mean? Well, we're going to look at that. We're going to look at what this means. Look at exercise number 7. All right, use the graph below to answer questions 7 and 8. It says, suppose the unnamed red graph on the left coordinate plane is the graph of the function g. Describe g as a vertical scaling of the graph y is equal to f of x. That is, find a value of k so that g of x is equal to k f of x. What is the value of k? Explain how you determined your answer. Okay, so you can't really... Here is my original graph. All right? It wants to know, what did we do to this graph in order to make it the way it is? All right? Well, we need to figure out what has happened. Notice my vertex is the same. All right? We have done, and it tells us to do a vertical scaling. So that means that I have multiplied my function by something to get my new graph. So the graph of g is a vertical scaling of the graph of f by a factor of 2. All right? So what we have done is we have multiplied our y values. All right? So basically what it's saying is I'm taking my y values and I need to multiply my y value by something. All right? To get the new y value. Because remember, our vertical scaling deals with the y's. All right? So the graph of g is a vertical scaling of f by a factor of 2. Okay? So therefore, g of x is going to be equal to 2 times the f of x. All right? By comparing the points on the graph of f to the points on the graph of g, you can see that the y values of g are all twice the y values of f. Okay? All right. So then let's look at number 8. Number 8 says, suppose the unnamed red graph on the right coordinate plane is the graph of the function h. Describe h as a vertical scaling of the graph of y is equal to f of x. All right, so we are doing a vertical scaling. All right, we're just looking at vertical. That is, find the value of k so that h of x is equal to k times f of x. Explain how you determined your answer. All right, so let's look at this. So we are looking at the graph on the right. All right. We want to know what has happened to my y values. All right, what has happened to the y values? Now look, here's y of f of x. What has happened to this? All right, what's happening to my y values? Well, in this case, the graph of h is a vertical scale of f by a factor of 1/2. Alright? So, I can say h of x is equal to 1/2 f of x. By comparing points on the graph of f to the points on the graph of h, you can see that the y values on h are all half the y values of f. Okay? So, if I am multiplying my graph by 2, then this is what happens. If I'm multiplying my graph by 1/2, this is what happens. Alright? Alright, let's talk about horizontal scaling. Alright? Use the graph below to answer questions 9 and 10. Alright, so go ahead and look at those graphs. Suppose the unnamed the unnamed function graphed in red on the left coordinate plane is g. Describe g as a horizontal scaling of the graph of y is equal to f of x. What is the value of k? Alright, so if you remember my horizontal scaling, it's going to look like this. F of 1/kx. Alright, so let's kind of compare. We're dealing with our x coordinates. Alright. So looking at this, looking at my x coordinates, so I go from 1 to 2. So I am multiplying by a factor of 2. So g is a horizontal scaling of f by a factor of 2. Alright, so what is that going to look like? Then that means that g of x is equal to f of 1/2 x. Alright? Suppose the unnamed function graphed in red on the right coordinate plane is h. Describe h as a horizontal scaling of the graph of y is equal to f of x. What is the value? Look at, I'm going from 1 to 1/2. So I am doing a factor of 1/2. So the graph of h is a horizontal scaling of f by a factor of 1/2. Alright, so that would look like this. H of x is equal to f of 1/1/2 x. So I need to multiply everything by 2. So h of x is equal to f of 2x. Alright. Alright. So let's kind of go back for just a second and look at these so I can explain them just a little bit more. I want to mark these up just a little bit. I didn't want to do a whole lot of marking on them to start with, but let's just kind of look at these for just a second. So I want to look at a point on my original graph. Alright, so let's look at on the original graph. That is a distance of y from the x-axis. Okay? Let's see what happens to that point now. Well, that point now comes up here. So what is happening to that point now? It has now gone double. So that is where I got the vertical factor of 2. Okay? Let's go over here for just a second. Let's look at, the inside is my original graph. This is my original point. Alright, that is a factor of 1, or y. Alright, and I tell you what, let's do this one. Let's do that one, okay, because it's a little easier to see. So that is a factor of y. Alright, that point now is down here. I actually took half of that, which is why we have a vertical scaling of 1/2. Alright, so hopefully that helped a little bit more. Let's go over here to these really quickly. Let's choose, remember we're dealing with x's here. So if I look at a point and I kind of pointed this out, there's my x. Well, that point now is here. So there is, oh, I'm sorry. Yeah, that's my original function. And there is my new function. So it's 2 times the amount. Alright, so I have a horizontal factor of 2. Alright, here's my original function. Let's choose this point right here. Right here. Alright, my original function is on the outside, and that was x, and this time it's now half of that. Okay? So hopefully that kind of helped a little bit in explaining how I got the scaling factors here. A dilation at the origin of d of k is a horizontal scaling by k is greater than 0, followed by a vertical scaling by the same factor k. In other words, this dilation of the graph of y is equal to f of x is the graph of the equation y is equal to kf of 1 over kx. Alright, so let's just kind of talk about this. If a dilation of a scaled factor is both horizontal and vertical, then I need to combine both of these equations. Alright, which is now why I have this equation. Because it is showing me that I am doing a vertical scale and a horizontal scaling. Alright? So make sure you understand that. When one figure is a dilation of another figure, the two figures are similar. A dilation at the origin is just a particular type of dilation transformation. Alright? So we're going to talk about just a little bit about a dilation. Alright? Last couple of questions here. Let f of x equal x squared and let k equal 2. Write a formula for a function g that results in dilating f at the origin by a factor of 1/2. Alright, so let's talk about this for just a second. It says that I have k is equal to 2, and I want to do a dilation by the factor of 2. Alright, so let's go back to this equation here. I am going to plug 2 in for k. So my y is equal to k of f f of 1 over kx. So if k is equal to 2, all right, then I'm going to do y is equal to 2f of 1/2 x. All right. Now, there's my function of this. Since we know that f of x is equal to x squared, I can now substitute that in. All right? It tells me that f of x is equal to x squared. So I'm now going to substitute that in to this. All right? So I get 2 times 1/2 x, and I want to square that. Well, that would be 2 times 1/4 x squared. Well, 2 over 4 is 1/2, so g of x is going to be equal to 1/2 x squared. What would the results be for k is 3, 4, or 5? And what about k is equal to 1/2? Well, let's go ahead and look at if k is equal to 3. So I would get y is equal to 3 f of k, or 1 over 3x. Plug in x squared. Y is equal to 3 times 1/3 x squared. All right, so that would be 3 times 1/9 x squared. So g of x would equal 1/3 x squared. If k was equal to 4, I think you can kind of see the pattern. Y is equal to 4 f of 1/4 x. I get 4 times 1/4 x squared. 4 times 1/16 x squared. So I get 4 over 16, which is g of x would equal 1/4 x squared. Bet you can figure out what 5 would be. If k was equal to 5, g of x would be equal to 1/5 x squared. All right, let's look at k is equal to 1/2 really quickly. Y is equal to 1/2 f of 1 over 1/2 x. Well, that would be y is equal to 1/2 f over 2x, or times 2x. All right, plug that in. I would get y is equal to 1/2 times 2x squared. So that would be y is equal to 1/2 times 4x squared. 4 times 1/2 is 2. So g of x would be 2x squared. All right. So are all parabolas similar? All right, so based on this example, we can conclude, what can we conclude about these parabolas? We can conclude that they are all similar to one another because they represent a dilation of the graph at the origin. All right, so is this enough to prove that all parabolas are similar? No, we've only proven these specific parabolas similar. So how can we prove all parabolas are similar? Well, we would have to use the pattern to observe others and make generalizations and algebraically show that it works. All right? So can we state that all parabolas are similar? Without further generalization, further study, no, we can't. but we can show that if they have a pattern, that there are certain types that are similar. Alright guys, that's the end of lesson 35. Have a great rest of your evening.